All right, let's get right into it. You know, your computer's CPU is an absolute beast. But here's the thing, it can really only do one single thing at any given microsecond. So how in the world does it manage to play a video, run a background scan, and keep all your tabs open without melting? Well, it all comes down to a really clever system called CPU scheduling. It's basically the operating system's secret sauce for creating the illusion that it's a master multitasker. I mean, really think about it. When you're deep in a game, you want all the power going to that, right? The last thing you need is some random update causing a massive lag spike at the worst possible moment. That smooth experience you're having, it's not an accident. Your computer is making thousands of tiny decisions every single second about what's important right now and what can wait a little bit. You know, the best way to picture this whole thing is to imagine a tiny, super fast traffic controller living inside your operating system. We call it the CPU scheduler. And its entire job is to direct all the different programs and processes that are screaming for attention. It needs to be efficient, it needs to be fair, and it needs to be fast. But as we're about to see, there are a couple of very different ways to manage all that traffic. Okay, so let's start with the first method. This one is all about structure, rules, and being very, very rigid. Think of it like creating strict, unchangeable lanes on a highway for different kinds of cars. This approach is called multi-level queue scheduling, or just MLQ for short. The idea behind it is actually pretty simple. Not all tasks are created equal. So why not sort them into different groups from the get-go? It's kind of like sorting your mail into different bins before you even start reading it. So here's how it breaks down. This system might create a super high priority queue for critical system stuff, a middle one for things you're actively doing, like clicking your mouse, and then a low priority queue for big background jobs, like a system backup. A process gets assigned to one of these queues, and now this is the most important part, it is stuck there permanently. It cannot move. And the system has one golden rule, and it's absolutely ruthless. The CPU will only look at the medium priority queue if the high priority one is completely, totally empty. And it'll only glance at the low priority queue if the top two are empty. If a new high priority task shows up, it will literally interrupt a lower priority task, kick it out, and take its place immediately. Now, this sounds super organized, and hey, it is. But this extreme organization, this strictness, leads to a really big fundamental problem. So let's zero in on that disadvantages column. See that word right there? Inflexible? That's the whole issue. Because a process can't move between queues, the system has no way to adapt if it makes a mistake. If a background task suddenly becomes really important, well, too bad, it just has to sit and wait its turn. That inability to move is the central flaw in this whole design. And this, of course, leads to a really powerful question. What if the scheduler could actually learn from its experience? What if it could notice that a process is taking a really long time and maybe adjust its priority? What if these tasks weren't just trapped in their lane forever? And that very question brings us to a much smarter, way more dynamic solution. It's one that takes the original idea and adds a brilliant twist, a feedback mechanism. This is the multi-level feedback queue, or MLFQ. Now, it starts with the same idea, multiple levels of queues, but it adds one absolutely game-changing feature. Processes can move between them. Their priority isn't carved in stone anymore. It's dynamic, and it can change based on what the process actually does. And honestly, this slide tells the entire story in just 4 words. We're moving from a fixed assignment system in MLQ to a dynamic movement system in MLFQ. This is the evolution from a simple, dumb sorting hat to a smart, adaptive system that learns as it goes. So if you remember one thing from all of this, let it be this mantra. In MLQ, you're assigned and you are stuck. In MLFQ, you can move and you can adapt. It's like the system is watching how you drive and can move you to a faster or slower lane to keep the whole highway flowing smoothly. Okay, so this smarter system sounds great, but how does it actually work? I mean, how does it decide when a process should be moved and where it should go? So here's where the feedback comes in. Every single new process starts at the very top in the highest priority queue, and it gets a tiny little burst of time on the CPU. If it finishes super quick, like processing a mouse click, perfect. It's done, it's out. But if it uses up its entire time slice and it's still not finished, the system learns something. It learns, hey, this is probably a longer, beefier task. So what does it do? It demotes it. it kicks it down to a lower priority queue, which usually gives it a longer chunk of time to work with. To really see how cool this is, let's follow one specific process. Let's imagine it's a big, heavy task that needs a full 40 seconds of CPU time. We're going to watch its journey as it travels through this feedback queue system. Okay, watch this. It starts in the top queue, Q1, gets its 2 seconds, but it's not done. So boom, the system demotes it to Q2. There it gets a bigger slice, 7 seconds. Still not done. Demoted again. It chews through 12 seconds in Q3, then a whopping 17 seconds in Q4. Every single time it fails to finish, the system pushes it further down the priority list, correctly figuring out that this is a long, background job that can be worked on when nothing more important is happening. So, in the end, our 40-second beast of a process got interrupted and demoted a grand total of 4 times. The feedback loop worked perfectly. It quickly filtered this long-running task away from the top-level queues, which keeps them wide open for all the short, important, interactive jobs that make your computer feel fast and responsive. So MLFQ just sounds better in every way, right? It's adaptive, it's smart, it's flexible. It seems like the clear winner. Well, like any good engineering solution, all of that intelligence comes with a cost. And here it is. MLFQ is by a long shot the most complex scheduling algorithm to design and get right. All of that tracking, moving, and reprioritizing, well, that's extra work that the CPU has to do. It's thinking time that isn't spent on your actual tasks. We call that overhead. And getting all the little details right, like how long the time slice should be for each queue, that requires a ton of careful tuning. So its greatest strength, flexibility, is also the source of its biggest headache, complexity. Ultimately, the whole thing really just boils down to this one simple trade-off. The simple, rigid MLQ system offers you rock-solid predictability. You always know exactly how a process is going to be treated. The complex, dynamic MLFQ system gives you intelligent adaptability, a scheduler that actually learns and responds to what's happening in real time.